Okay, in this screencast we're going to look at the instantaneous rate of change. We're in a section of the course known as the rate of change, and it introduces us to a huge field of mathematics known as calculus. So we're starting off with the basics, and we've looked at rates of change, and I've made a couple of notes here, so I'd like you to take them down. And if I just read them through, so our heading is instantaneous rate of change. Rates of change are either constant in the case of a line, or variable in the case of a curve. So in the case of a line, well, you can measure the gradient, and the gradient is the same no matter what section of the line I select. So that's defined as a constant rate of change. The rate of change, or the gradient, does not change. Or the rate of change can be variable in the case of a curve. So it's by definition with a curve, the rate of change is variable. It's changing all the time. So at this point here, it's a positive rate of change. It's going up. X and Y both going up, but it flattens out here, so it's less, but still positive. Here, actually, the rate of change is 0. Now it becomes negative, steep negative, 0 again, positive again. So it's all, look, the slope, or the rate of change, is always changing, and so it's variable with curves. Okay, so that leads us to think then about how to calculate the rate of change. It's easy to calculate the rate of change of a line. You just have to calculate the gradient, rise over run. We've encountered that. But as it says here, as I say here, calculating the rate of change of a curve is more problematic. We can calculate the average rate of change, and we've done that through the calculation of, let's say we've got a curve here like so, and we want the rate of change, and we can calculate the average rate of change between 2 points by taking those 2 points, drawing a line between them, and then calculating the gradient, the rise over run. So that calculation there, rise over run, will be equal to the average rate of change. Average rate of change between these 2 points, between P and Q, average rate of change. So we can calculate the average rate of change between 2 points. That's okay, and we've done that in the last. We did that in the last section. But what about the rate of change at a specific point, which is known as the instantaneous rate of change? So let's now say I don't want this average rate of change business. I actually want the rate of change at P. What is it? What is the value of it? What's the number of it? I want a numerical value to the rate of change of at P specifically, or at Q maybe, or over here. So that's where we're turning our attention now, as to how to find that rate of change. Okay, I'm going to go to a bit of software here that I think is quite nice. Now, to just demonstrate the difference between the average rate of change and what we're moving towards, the instantaneous rate of change. Now, what I'm going to concentrate here is the point A, which has coordinates 2, 11.98. This is the curve, the parabola, is the function y equals 3x squared. So that's 3x squared there. This is a point on the parabola, point A, and has coordinates just there, 2, 11.98. And this is the point B, which currently has the coordinates 4.95, 73.53. Now we could find the average rate of change by calculating the gradient A to B. Now that's something that won't be a problem for us. I think, in fact, we've got, it's just there, m equals 20.85. I think that is our there it is there. So for every unit we go across, you see a run of 1 and a rise of 20.85. So the average rate of change from A to B on this curve is 20.85. Okay, as B moves, so that's the average rate of change. Let's say that we're interested in the instantaneous rate of change at A. Okay, so what I'm going to need to do is bring this back closer to A. Now you can see the gradient's changing. At the moment now, it's the average rate of change from A to B is 16. I don't want that. I want the instantaneous rate of change at A. Now, where do you think that is? Now, at the moment, that's a very, very short segment AB, and it's 12.24 as my average rate of change. But if I bring B right back so it sits right on top of A, which is a pretty hard task. If I sit that right on top of A, then what I have is the instantaneous rate of change. If I set that right on top of A, then I don't have a segment anymore. I've got what's known as a tangent to the curve. And you can see I'm having a little bit of trouble doing that. I'm pretty close there. That'll do. So that line now is not a chord anymore, or a point that joins 2 points on my curve. It's what's known as a tangent because it touches at 1 point only. Now the gradient of that line, that tangent at the point A, that is defined as the instantaneous rate of change of this curve, Michael-Sweck's curve. Remember, that's the subject of it. That's what we're looking at. The rate of change, the instantaneous rate of change of this curve at that point A is equal to the gradient of this tangent here. Okay, do you think you can remember that? So let's now go back to what we're looking at here. The instantaneous rate of change, and we just need to make a note of that, is the gradient of the tangent at the designated point. So the instantaneous rate of change is equal to the gradient of the tangent to the curve at the designated point. Does that make sense? The instantaneous rate of change is equal to, of a curve, I should write of a curve, is equal to the gradient of the tangent to the curve at the designated point. So the instantaneous rate of change of a curve, instantaneous rate of change of a point on a curve. It gets a little bit tongue-twisted, but it's probably most easily demonstrated, as I did a moment ago, by just looking at a graph. So if we have a look at, say, just some curve here, then if we're going to take a point on that curve, let's take a point just here, then the gradient of this curve at that point, the instantaneous rate of change of this curve at that point is the gradient of the tangent to the curve at that point. So let's just make a note here that is a tangent to the curve at point, let's call that point A. That's the tangent to the curve at point A. And we can also make the note that, therefore, the gradient, not the gradient, the tangent, the instantaneous rate of change, the instantaneous rate of change of the curve at point A is equal to the gradient of the tangent at A. Okay, so hopefully that's clear now. The instantaneous rate of change is at point A of this curve. We need to draw a tangent. So let's say we're interested, let's just to make sure we've got it, another curve here, and it's doing something like this. Then if we're interested in this point here, what's the rate of change of the curve? What's the instantaneous rate of change of the curve at that point? What we need to do is construct a tangent at that point. Now a tangent is just where it's a line that just glances on the curve at that point. So that tangent will move around. As that point moves, the tangent would move. So if we got the point around to here, then the tangent will look like that. So it's a point that just glances on the curve and intersects just at the one point, just in the immediate locality of that point. So as this point moves around the curve, so the tangent moves, and it's the gradient of that tangent that defines our instantaneous rate of change at that point. So if we calculate these green gradients, then we have the rates of change of the curve at those points. Okay, I think that defines it adequately, hopefully. The next thing we need to do, therefore, is to just be able to calculate the gradient of those tangents. So, for example, if pause. Okay, so picking up the challenge now to find out what the instantaneous rate of change is at a certain point on a curve. Just having a look here, I've sketched y equals x squared out quite quickly and put a point down 2, 4. We want to find the instantaneous rate of change of this curve at that point 2, 4. Now, because we only have one point, we can't calculate the gradient of the tangent. I could draw a tangent here, but I don't know what the other points are. So what we end up doing, just to get a little approximation, you can imagine if I drew a tangent in here, that's going to be pretty close. It's going to be pretty close to, if I, so there it is in green, if I put another point on this curve really close by, say at 2.1, and drew the line from 2 to 2.1, then the gradient of that tiny little black line there that I've just drawn, between 2 and let's say the other point here I've got is 2.1, and 2.1 squared we'll figure out as 2.1 squared. That gives us 4.41. So if I go back to 4.41, okay, so the gradient of the black line, you can see that black line that connects 2.4 to 2.1, 4.41, that's going to be really, really close to the value of the gradient of the green line, which is the instantaneous rate of change, 2.4. So therefore, we approximate. So we approximate the instantaneous rate of change at 2.4 by calculating the gradient of the line connecting 2.4 to 2.1, 4.41. Now I could have used 2.01. I could have used 2.001. The closer I get, the closer I make those orange dots, then the closer it will be, or the better the approximation will be to the gradient of that green tangent. But I can work this gradient out. This one here, I can take it to be 2.1. Sorry, that's the x difference. That goes underneath. The y difference is 4.41 minus 4, and the x difference is 2.1 minus 2, and y2 minus y1 on x2 minus x1. So I get 0.41 over 0.1, which equals 4.1. So my rate of change, instantaneous rate of change at 2.4 is approximately 4.1. I'm getting 4.1 from my calculation of that gradient there. Okay, that's enough for this screencast, and it should be enough to get us going on exercise 18D. Have fun with that. See you soon.